Alright, you should have your new set of notes out in front of you. And we're going to start with something that is familiar to you, which is graphing, and that's why we reviewed graphing a little bit yesterday, or today actually, so that this might be a little bit easier for you. But we'll review the basics of exponentials by doing the properties, and then that you also in Algebra 1 learned some of the real-life applications that resulted from the types of patterns that exponentials give you. In this unit, we'll be addressing some of the same ideas and concepts, but at a deeper level. So this standard focuses in on the graphical representation of exponentials. So we're just going to be really talking about the graphs at this point. Definition of an exponential function. The general form looks like this, where A affects how steep your graph is or how shallow your graph is. B is your base. This is the value that tells you what percentage growth or decay you have. For example, in the book that we read about the rice, our base was 2 because the situation was doubling. So if our situation's tripling, then that would be a 3. So it tells you what's going on percentage-wise if it's doubling, tripling, halving, or whatever. The H moves your graph left or right, and then K moves your graph up and down. The properties and qualities of a basic exponential graph, and that would be one that doesn't shift, is that, or one quality or property, is if the base is less than 0. Oh, I'm sorry, not less than 0. If it's less than 1 but greater than 0. It can't be less than 0. So let's draw it like that. Okay, so if your base is less than 0 but less than 1 but greater than 0. I feel like I need to rephrase that whole thing. Scratch that out. Okay, let me try. If base is between 0 and 1. Okay, that's a better way to put it. Basically, if you're looking at a fraction, then you have exponential decay. And I'm not going to re-talk about that because I know that you guys have been introduced to that before. So exponential decay is a term that you guys should already know. If your base is greater than 1, then you have exponential growth. And we'll get into more and more why that happens, or why that base value is so important to tell us what's going on in the situation. But for right now, that's just a generality that applies every case. Okay, the second thing is that the graph will follow a horizontal asymptote. Now, this is a phrase that you probably should remember from Algebra 1, but if you don't, an asymptote is like an invisible fence or boundary that the graph does not cross. If you're working with a basic exponential graph that doesn't shift up or down, then your asymptote is the x-axis and just kind of follows the x-axis forever and ever, but never actually crosses it. And again, we'll get into more why that happens in a later section. Okay. And then the third thing that we always refer to is the domain. Okay. The domain will always be all reals for an exponential function because you can plug in any x you want, because anything can be raised to a negative power or to a 0 or to a positive power. But your range is going to be affected by how much you shift. So you can be greater than or equal to whatever the k value is. If you don't shift up or down, then it's just the x-axis. And I'm sorry, it should not be equal to. Because that k value is going to be where the asymptote is, and you can't actually touch the asymptote. So it's just going to be y value is greater than k. Okay, the 4 different kinds of graphs that you'll see look like this. Now, these are the 2 most common. This would be called exponential growth. This is exponential decay, because you decrease over time quickly. This one you increase over time quickly. And then what happens here is this is where you have an exponential growth with a negative a value. And this is exponential decay with a negative a. All the way back up here at the very beginning, when you have an a value in front, it's like maybe 2 times 3 to the whatever, that number in front, if it is negative, what it's going to do, it's going to take that regular graph of yours and flip it over the x-axis. So it's going to reflect it. So that sometimes happens with your exponential growth and decays, that they look like that. Just to make you aware. Okay, go ahead and flip. And then steps to graphing exponential functions. Much of our graphing has revolved around these 3 steps. First step that we're always going to do here when we have an h and a k in play is we're going to start by labeling the transformations. After you're done labeling the transformations, you're going to make a small table of values. And because we can plug in anything we want, we're going to use the 3 easiest ones, -1, 0, and 1. The third step is to draw your points, shift, and then before we actually draw the curve, we're also going to draw in the asymptote, where that's located. Remember, it always starts the x-axis, and so if you shift up or down, that thing always shifts with the graph. After you draw the asymptote, then you're going to connect the points with a smooth curve, being careful to follow the asymptote. Okay, so looking at example 1, in this first graph here, we're going to graph y equals 2 times 3 to the x minus 2 plus 1. The other thing that I should probably mention here is when you're dealing with exponential functions, you know it's an exponential because your variable is in the exponent. That's what makes it an exponential function. That's something that I forgot to mention earlier. Okay, so if you were just asked to graph this and I didn't tell you it's an exponential, you would recognize it as an exponential because the variable's in the exponent. Alright, let's go ahead and label the transformation. This 2 is going to make my graph move to the right 2. This 1 is going to make my graph move up 1. And then in my small table of values, I'm going to use -1, 0, and 1. Now this is part of the reason we reviewed properties of exponents yesterday. When I plug in -1, remember we're drawing brackets around my y and my x. When I plug in -1, 3 to the -1 is the same thing as saying 1/3, because that -1 flips the 3 to the bottom. So 3 to the -1 is 1/3, and 1/3 times 2 is going to give me 2/3. 3 to the 0 is 1, because anything raised to 0 power is 1. So 1 times 2 would give me 2. When I plug in 1, 3 to the first power is 3. 3 times 2 is 6. So I'm going to plot those 3 points. Then I'm going to shift those 3 points to the right 2 and up 1. And then before I actually connect my curve, I need to know the fence that it's following, or the boundary that it's following, which is created by the asymptote. Now the asymptote is usually at the x-axis. Because I shifted up 1, that has also now shifted up 1. And since it's not actually part of my graph, it's just a guiding line, I'm going to draw it in as a dashed line to show it's not actually part of my curve. And then when you're drawing your curve, it follows the asymptote and then curves upward. Then we're going to label our domain and range. Domain is going to be all reals. Your range is going to be y values greater than the asymptote there, which is 1. And notice, again, because that's never going to actually cross the asymptote, you're going to leave off the equal to bar. Alright. Then let's do one here. Okay. This one, I'm going to make it an exponential decay, but I'm also going to make it flip. So just be aware of that. The 1/2, my base, is what makes it an exponential decay, because that means for every unit you go forward, your amount is being cut in half every time. So it's being reduced by 50% every time. But that negative a is going to make my graph flip. So instead of being a graph that looks like this, exponential decay, it's going to look like that, but it's going to be flipped over the x-axis. Now you don't have to physically do the flipping, because the table will take care of it. Just know that that's what it's going to look like. Alright, this 3 is going to make my graph move to the right 3. This is going to make my graph move up 2. Again, small table of values, -1, 0, 1. Now, keep in mind, when I plug in that -1 for the exponent, that -1 is going to take that fraction and flip it. It's going to reciprocate it. So 1/2 to the -1 is actually 2, and 2 times -2 is -4. When I plug in 0, anything raised to 0 power is 1. 1 times -2 is -2. When I plug in 1, 1/2 to the first power is just 1/2, and 1/2 times -2 is -1. So I'm going to go ahead and plot those 3 points. And then I'm going to take all 3 of those points there, and I'm going to shift them right 3 and up 2. And then the asymptote, again, was at the x-axis, but since I shifted up 2, that also shifted up 2. So before I draw my curve, I'm going to draw on the asymptote. Now keep in mind that this is the normal shape of an exponential decay, but it has now flipped. So when I draw on my curve, it's going to follow the asymptote and then curve downward, like that. Domain, it's all reals. Range is going to be y values less than, because now my whole graph is less than that asymptote, which is the value of 2. Okay. And then we're just going to get more practice today on, or tomorrow when you're in class, on each type of those. So you're going to get, ones that look like this. You're going to get ones that look like this. And then we're also going to make sure that we practice the other 2 types. So a regular exponential decay, and then one that's flipped that was a growth. So lots of practice with it.